Part 1. Preparing the 3D scan for mold design. Hello everyone and welcome back to the Mecproman channel. In today's video, I'm going to walk you through the complete process of designing a mold for a scan sculpture. Before we begin, I'd like to mention that in addition to SolidWorks, we also use two supporting software packages, Blender and QuickSurface. I'll explain the role of each one step by step. Let's start with Blender. The original sculpture provided by the client is an STL mesh model. Since it's only a mesh, we first need to prepare it before creating the mold. The first thing we do is create a new Blender file, delete the default objects, and import the STL model supplied by the customer. This is the original scan sculpture that we'll use throughout the mold design process. Before adding any thickness to the model, there's one very important step. If we switch to edit mode, you'll notice that some areas of the mesh have a very fine and dense topology. These regions usually produce high-quality surfaces later in SolidWorks. However, other areas contain much larger polygons and uneven mesh distribution. Those regions often lead to poor surface reconstruction and lower CAD quality. To solve this problem, we remesh the entire model. Back in Object mode, we open the Modifiers panel, choose Generate, and add the Remesh modifier. I normally use Smooth mode and then adjust the resolution according to my computer's performance. For example, a resolution value of 4 doesn't produce acceptable results. Increasing it to 6 gives us a better mesh, but it's still not accurate enough. A value of 9 is much better, although some sharp edges still need improvement. Personally, I prefer using a value of 10, which provides a much finer and more uniform mesh. Higher values can generate even better results, but they require a more powerful graphics card and additional processing time. Once you're satisfied with the quality, simply apply the modifier. Now, if we return to edit mode, you can clearly see that the entire sculpture has been rebuilt with a much denser and cleaner mesh. This greatly improves the quality of the surface reconstruction we'll perform later. The next step is adding thickness. Back in Object mode, we apply the Solidify modifier. Our target wall thickness is 10 millimeters, which is equivalent to 0.01 meters. We also keep the offset value set to 0. As you can see, Blender generates a uniform 10 millimeter shell around the sculpture. After applying the modifier, our work inside Blender is complete. Even if you're not familiar with Blender, you'll notice that we only use two modifiers throughout the entire process: Remesh and Solidify. Finally, we export the modified model as another STL file. I usually rename it to indicate that the model now contains wall thickness. Surface reconstruction in QuickSurface. Now let's move to the second software, QuickSurface. QuickSurface is responsible for converting our optimized mesh into CAD surfaces. We import the thickened STL file that we exported from Blender. Since the model was created using metric units, we keep the unit system set to meters before importing. The purpose of QuickSurface is to reconstruct smooth CAD surfaces from the mesh. Although this can technically be done inside SolidWorks, it's an extremely time-consuming and complicated process. QuickSurface performs the same task much faster and much more efficiently. The easiest way is to use the Auto Surface function. Initially, you can simply keep the default settings and click Preview to evaluate the result. If the generated surfaces don't meet your expectations, you can increase the quality settings. For example, change the quality from medium to fine and increase the target quad's control and feature detail values. Set feature detail to higher or even highest, delete the previous preview and generate a new one. With these settings, the reconstructed CAD surfaces become much cleaner and much more suitable for the next stage of the mold design process. As you can see, the result is now significantly better. The surface quality has improved considerably, and from my perspective, this reconstruction is now accurate enough to proceed. QuickSurface also provides analysis tools that allow you to compare the reconstructed CAD surfaces with the original mesh. You can evaluate the deviation between the two models and verify the overall accuracy of the reconstruction. For this project, the deviation is well within an acceptable range, so I'm happy with the result. Next, I simply hide the original mesh by turning off its visibility, and now you can clearly see the reconstructed CAD surfaces. At this point, I export the model directly to SolidWorks by selecting the SolidWorks export option and clicking Start. After the export is complete, we open the file in SolidWorks. As you can see, the software has converted the sculpture into a fully solid body. If I create a section view, you'll notice that it's now a complete solid model, exactly what we needed for the mold design process. There are still a few small areas where the reconstruction isn't perfectly smooth. For example, you can see some imperfections in these regions. However, this largely depends on the quality of your original mesh. For this particular sculpture, these small imperfections aren't critical, but if you need even smoother surfaces, there are several ways to improve the result. One option is to go back to Blender and increase the remesh resolution before exporting the model. Another option is to use Blender's Sculpt mode. Inside Sculpt mode, you can select the smooth brush, adjust its strength, for example to around 0.7, and gently brush over those rough areas to smooth the mesh before sending it to QuickSurface. In my case, I intentionally avoided modifying the customer's original scan. I wanted to preserve the scan geometry exactly as it was provided, so I chose not to smooth those regions manually. Of course, if you're working on your own project, you can absolutely spend more time refining the mesh before reconstruction. As I mentioned, because this was a customer's original scan, I preferred to keep the geometry as close as possible to the original data. Fortunately, these minor surface imperfections don't create significant problems during the mold design process, and they can easily be corrected later using the original sculpture geometry if necessary. Now, instead of recreating the entire mold from scratch again, I'll switch to the completed project file. I've already spent a considerable amount of time developing that model, so rather than repeating every step, I'll use the finish file to explain the remaining stages of the mold design process and walk you through the workflow in a much more efficient way. As you can see, I have opened the reference file for the mold piece related to the head. In fact, the references for all the mold pieces open in the same way once you follow the same process I used. Now you can see that I have worked on this file quite a lot, and I need to explain it step by step. If I roll back the model to this point, you can see that this is exactly the same file I explained earlier, the one we exported using Blender and QuickSurface. Here I created several reference surfaces. As you can see, I made sketches on different planes and then used SolidWorks surface tools, especially planar surface, to generate these surfaces. These surfaces define the areas where I plan to separate the mold. Since this sculpture has a very complex form, deciding the parting boundaries is not simple. So first you need to mentally divide the sculpture into different mold sections. Based on those imagined separation zones, you create surfaces that will act as mold-splitting boundaries. If I move forward through the feature tree, you can see that all these surfaces define the parting lines of the mold sections, and as you can guess, the final mold pieces were generated based on these surfaces. Next, we move to the split feature. Using the split command, we can select these surfaces in the main body of the sculpture and then cut the sculpture body according to these boundaries. Now you can see the cut lines. If I hide the surfaces, you can clearly see where the body has been split. All of these cuts were created using the split command. The next step is to combine the separated bodies. After the split, some pieces overlap or intersect in different areas, so we need to organize and merge them properly. For example, I combine the pieces related to the head section, then I combine the front part of the head. After that, I combine the right half of the torso, based on the assumption that if the mold is designed this way, it will be easier to open and remove. One very important point is to make sure the parting lines do not fall into negative angles or undercut areas. For example, if I had moved this line slightly forward or separated the mold from this lower area, removing the mold from the left side could have been very difficult. That is why I tried to define the parting line along the highest possible boundary. Then I continued combining the left side sections and other mold regions step by step. As I move forward, you can see the mold pieces taking shape. After that, I created a series of extrusions around the mold pieces. These extrusions form the connection flanges around each mold section. These flanges are used to connect the mold pieces together. As you can see, I created these connection flanges piece by piece. In areas where I needed to hollow out part of the mold, I inserted the original sculpture body into the file. This is the original scanned sculpture model, without any thickness applied to it. The reason I brought this original sculpture body into the center of the mold was to use it as a subtraction body. If I isolate it, you can see that it is solid, but the mold needs to be hollow inside, So I used the original sculpture model with the combine greater than subtract command to remove its volume from the inside of the mold. As a result, the internal cavity of the mold is created. I repeated this process in several areas so that each mold section would have the correct internal hollow space. You can see that in some places the subtraction has already been done, while in other areas it has not been applied yet. Wherever small corrections were needed, I used SolidWorks solid editing tools to clean up the geometry and create more continuous surfaces. In some areas, the flanges were not perfectly aligned, so I had to manually adjust them using SolidWorks features. In this way, I gradually shaped each mold piece and moved forward step by step until the mold sections were fully developed. As you can see, at this stage I created the connection flanges around each mold section and completed the assembly interfaces. During the design process, I realized that some additional parting lines would make the mold much easier to remove after casting. For example, in my original design, I hadn't planned to separate the mold around the knee area. However, as the project progressed, it became clear that adding a new separation line there would significantly simplify demolding. To achieve this, I created several additional reference surfaces and used them to define new parting boundaries. I don't remember exactly which surface feature it was in the feature tree, but the overall idea was to introduce new splitting surfaces wherever they improved the mold removal process. This allowed me to divide those regions into additional mold sections and complete the overall mold design. Any unnecessary bodies were simply removed using the delete body feature. Once everything was finished, each mold section existed as an individual solid body. At this point, I could simply right-click each body and choose Insert into New Part to save every mold piece as a separate SolidWorks part file. If you prefer, you can also create all the alignment holes and fastener features at this stage. Personally, I chose a different workflow. After saving each mold section as an individual part, I added the locating pins, alignment holes, and fastening features separately inside each part file. Let's move to the final assembly. Here you can see the complete mold assembled from all the individual components. If I switch back to the default configuration, you'll notice something different. I actually created a lightweight assembly configuration where all the bolts, screws, and threaded inserts are suppressed. This keeps the assembly much lighter and makes it easier to demonstrate the design without slowing down SolidWorks. In the default configuration, however, you can see all the hardware installed. For the threaded inserts, the installation process is straightforward. We simply heat the insert using a soldering iron and press it into the printed plastic. Once it cools down, it becomes permanently embedded inside the mold. There's one more important point I'd like to mention. The client wanted every mold section to be fully 3D printable. I recommended printing the molds using TPU filament instead of a rigid material. The reason is that TPU is flexible. When you're removing the mold from the finished casting, that flexibility becomes a huge advantage. Although we carefully design the parting lines to minimize undercuts and make demolding easier, there are still a few areas where removing the mold can be challenging. For example, imagine trying to remove this section. As you pull it downward, the sculpture's arm could interfere with the movement and cause the mold to catch. Because TPU behaves more like rubber, you can gently flex the mold while slightly rotating or tilting it, making removal much easier without damaging either the mold or the sculpture. These small design decisions can make a significant difference in the success of the final mold. I hope you enjoyed this tutorial and found it useful. If you did, don't forget to like, subscribe, and leave a comment below if you have any questions. I'd be happy to answer them as quickly as possible. Thank you for watching, and I'll see you in the next video. Happy designing,